7.5 billion years. That's how long this object's surface has been exposed to cosmic radiation. Earth didn't exist yet. The sun hadn't formed. Complex life was still 4 billion years away from emerging anywhere in the universe. And during all that time, 7.5 billion years, this object was traveling through the darkness between stars, getting bombarded by cosmic rays at full intensity. No magnetic field to protect it, no atmosphere to shield it. Just raw, unfiltered radiation, second after second, millennium after millennium, for longer than our entire solar system has existed. And now that ancient crust is evaporating, sublimating under our sun's heat, revealing something underneath that doesn't match any known chemistry, chemical signatures that shouldn't exist, isotope ratios that break our models. And the scientific community? They're minimizing it, calling it unexpected but explainable, saying we need more data before conclusions. But what if the data we already have is screaming something they don't want to hear? Let me tell you what we're actually looking at here, because the story of 3I Atlas's irradiated crust is the story of time itself written in ice and radiation. This isn't just about one comet. This is about what happens when matter survives in the most hostile environment imaginable for geological timescales. And what we're discovering is that the journey changes everything. The object that left its home star system 7.5 billion years ago is not the same object that arrived here. The crust has been transformed into something new, something we've never seen before, something that raises questions about every assumption we've made about interstellar objects. The James Webb Space Telescope detected it first, back in August 2025. When 3I Atlas was still far from the sun, Webb's near-infrared spectrograph analyzed the comet's surface composition. Standard procedure. They were looking for water ice, carbon dioxide, methane, the usual suspects in cometary chemistry. What they found was unusual carbon dioxide abundance. Not just abundant, dominant. The comet's surface had 10 times more CO2 relative to water than any solar system comet we'd ever measured. That was the first hint that something was different. But the real revelation came when they analyzed the isotope ratios. Carbon has two stable isotopes, carbon-12 and carbon-13. Normal ratio in solar system is about 89 carbon-12 atoms for every one carbon-13. This ratio varies slightly between objects depending on where and how they formed, but it stays within predictable range. 3I Atlas, the ratio was 73:1. That's not a slight variation. That's a fundamental deviation suggesting formation environment radically different from anything in our solar system, or suggesting something happened to the carbon during its 7.5 billion year journey. Dr. Ryan Majolo at NASA's Goddard Space Flight Center led the analysis. His team spent 3 months building computer models, simulating what happens to ice when it's bombarded by cosmic rays for billions of years. The modeling was based on earlier work studying radiation effects on solar system comets, but scaled up to interstellar timescales. What they found was shocking. After approximately 1 billion years of exposure, the transformation is complete. The outer 15 to 20 meters of the comet becomes fundamentally altered. Carbon monoxide transforms into carbon dioxide. Crystalline ice structure changes. Chemical bonds break and reform into new configurations. The surface becomes a radiation-forged crust that no longer represents the original material. Think about what that means. When astronomers look at 3I Atlas and analyze its spectrum, they're not seeing material from its home star system. They're seeing the product of the journey. It's like trying to understand ancient pottery by analyzing the glaze instead of the clay. The glaze tells you about firing process, not about the original material. 3I Atlas's crust tells us about interstellar space, not necessarily about the environment where it formed. As Majolo put it in his Nature paper, published October 15th, 3I Atlas is now a product of its interstellar journey, not of the place it came from, at least on the outside. At least on the outside. That qualifier is crucial because underneath that irradiated crust, pristine material might still exist. Material that has been protected by the radiation-damaged layers above it. Material that could tell us about another star system as it was 7.5 billion years ago. That's what scientists were hoping to find when the comet approached perihelion and solar heat began to erode the surface. That's what they thought would happen. The crust would sublime away, revealing ancient ice underneath, giving us a window into conditions around a distant star from when the universe was half its current age. But that's not what happened. What happened was far stranger. November 3rd, 2025. European Southern Observatory's Very Large Telescope in Chile conducted high-resolution spectroscopy as the comet approached perihelion. They were specifically looking for changes in chemical composition as surface layers sublimated. Dr. Sofia Ramirez led the observation team. Her initial analysis, released November 7th, noted surprising consistency in spectral features despite significant mass loss. Translation: the chemistry wasn't changing even though the surface was evaporating. The crust was coming off, but what was underneath looked chemically identical to the crust itself. This makes no sense under standard model. If crust is radiation-damaged layer and interior is pristine ice, their chemistries should be different. Damaged layer should show altered isotope ratios, changed molecular structures, new compounds created by radiation. Pristine interior should show original formation chemistry. Transition from crust to interior should be obvious in spectroscopic data. It wasn't. The consistency suggested either the radiation damage penetrated far deeper than models predicted, or the entire object has uniform composition throughout, or something else is happening that models don't account for. Dr. Ramirez's team ran additional observations November 8th through 10th. Same result. Chemical signatures remained constant as brightness increased by factor of 2.1. The comet was producing enormous amounts of gas, 5.7 times 10 to the 28th water molecules per second by November 10th, but the isotope ratios weren't changing. Carbon-13 to carbon-12 held at 73 to 1. Oxygen isotope ratios showed similar consistency. This uniformity across massive outgassing event is unprecedented in cometary science. Then came the ammonia problem. November 12th, Gemini Observatory in Hawaii detected ammonia spectral lines. Ammonia shouldn't be there. It's not stable in outer regions of stellar systems where comets form. Ammonia sublimes at much warmer temperatures than water or CO2, so it only exists in very cold environments, like the outer edges of planetary systems beyond the ice line. Finding ammonia in 3I Atlas suggests it formed in extremely cold region of its home system. But if it formed that cold, why does it have such unusual isotope ratios? Cold formation environments produce specific isotope signatures that 3I Atlas doesn't match. The ammonia presence contradicts the isotope data. Both can't be true simultaneously under standard formation models. Dr. Ramirez tried to reconcile the contradiction. Her working hypothesis presented at December Astronomical Conference in Washington. Perhaps the object formed in a protoplanetary disk with very different chemical gradients than our own solar system. Perhaps the star it formed around had unusual elemental abundances that created non-standard isotope distributions. Perhaps, and here she paused, choosing words carefully. Perhaps we're seeing combination of formation chemistry and radiation alteration that creates signature we haven't encountered before. We need more data to distinguish between possibilities. But more data isn't coming, not the kind that would resolve these questions. 3I Atlas made closest approach to Sun November 7th. Perihelion distance, 0.98 astronomical units, barely closer than Earth's orbit. After perihelion, the comet began receding. By December, it was too faint for detailed spectroscopy from ground-based telescopes. By January 2026, only largest telescopes could detect it at all. The window for gathering critical data closed before the community could fully analyze what they were seeing. That's unusual. Normally, when scientists encounter anomalous object, they mobilize resources. They coordinate observations across multiple facilities. They write rapid response proposals for large telescopes. The astronomical community is generally efficient at capitalizing on rare opportunities. But with 3I Atlas, that mobilization never fully materialized. Some observers attempted follow-up. Amateur coordination did happen, but the large-scale professional campaign that should have occurred didn't. Why not? Dr. Ramirez offered explanation in private conversation. We tried. We submitted proposals to Hubble, to Webb, to ESO's Director's Discretionary Time Program. Some were approved, but with long delays. Some were rejected as not demonstrating sufficient scientific urgency. By the time some observation windows came around, the object had faded below useful signal-to-noise thresholds. It felt like we were fighting uphill battle to get resources allocated. She wouldn't elaborate on who or what created that uphill battle, but the pattern suggests institutional resistance to dedicating premier facilities to object that was raising uncomfortable questions. The isotope ratios are what make people uncomfortable, because there are really only two explanations. First, the object formed in stellar environment so different from ours that our formation models don't apply. This means our understanding of planetary system formation is less universal than we thought. Every model we've built is based on studying our solar system plus observations of protoplanetary disks around young stars. We assume basic chemistry is consistent across galaxy. Finding object with fundamentally different isotope signatures challenges that assumption. It suggests stellar systems can produce chemistry outside our model space. That's unsettling to theorists who've spent careers building those models. Second explanation, the isotope ratios aren't natural. They result from process other than stellar nucleosynthesis and planetary formation. What process? Artificial isotope separation. Technology. If you wanted to build long-duration spacecraft using ice as radiation shielding and propellant, you might engineer specific isotope ratios for performance reasons. Lighter isotopes sublime at slightly different temperatures than heavier isotopes. Controlling isotope mix gives you control over outgassing behavior. This is speculative, but it's not crazy. Isotope separation is routine industrial process on Earth. We do it for uranium enrichment, for medical isotopes, for scientific applications. Advanced civilization would presumably have much better isotope separation technology than we do. If 3I Atlas were artificial, engineered isotope ratios would be plausible design feature. Nobody wants to say this publicly. It's career suicide to suggest astronomical object is artificial without overwhelming evidence. But in private conversations, the question comes up. Why are the isotopes wrong? Why is ammonia present where it shouldn't be? Why did chemical composition stay constant during massive outgassing event? Why does 7.5 billion year radiation damage not penetrate deeper than 15 to 20 meters when models say it should go much deeper? Each question has possible natural answer, but taken together, the pattern is strange. Dr. Martin Cross at Oxford studies cometary formation. I asked him directly, could these observations be consistent with artificial object? His response, consistent? Yes. Diagnostic? No. Everything we're seeing could result from natural formation in unusual environment, plus radiation damage we don't fully understand. But if someone asked me to design interstellar probe using comet disguise, I'd engineer it very much like what we're observing. Uniform composition to avoid spectroscopic changes during sublimation. Isotope ratios optimized for thermal management. Ammonia for low-temperature propulsion. Radiation crust providing natural shielding and stealth. It would work. Does that mean 3I Atlas is artificial? No. Does it mean we should consider the possibility? Intellectually, yes. Professionally, that's much more complicated. Professionally complicated. That phrase captures everything about this situation. The data is ambiguous. The implications are enormous. The institutional incentives all favor conservative interpretation. Say it's natural comet with unusual properties. Say we need more data. Say further study is warranted. These are safe positions. They don't generate controversy. They don't threaten funding. They don't invite ridicule from colleagues. But what if conservative interpretation is wrong? What if 7.5 billion-year-old crust is trying to tell us something that we're refusing to hear because hearing it would require acknowledging possibilities we've been trained to dismiss? The crust evaporated. We saw what was underneath. It doesn't match our models. At what point does unusual but natural become, we need to seriously consider alternatives? That's the question the scientific community is avoiding. And the longer they avoid it, the harder it becomes to address honestly when, if, definitive evidence eventually emerges. The crust is gone now, sublimated into space. The window closed. We'll never get another chance to study 3I Atlas at perihelion. It's receding into interstellar space, fading into darkness, carrying its secrets with it. Did we miss something critical? Did institutional caution cost us chance to make most important discovery in human history? Or are we overthinking ambiguous data from unusual but ultimately natural object? These questions won't be answered, not for 3i Atlas, but next interstellar visitor. That's when we'll learn if we're capable of recognizing something truly anomalous, or if our frameworks are so rigid that we'll rationalize away any evidence that doesn't fit. The billion-year crust showed us the limits of our models. What it didn't show us is whether we're capable of transcending those limits when data demands it. The physics of cosmic ray bombardment is brutal and precise. High-energy protons and atomic nuclei traveling at near light speed slam into surface molecules, breaking chemical bonds, displacing atoms, creating cascades of secondary particles. Each impact releases energy equivalent to thousands of simultaneous chemical reactions. Over millions of years, this transforms the surface structure at molecular level. Over billions of years, it rewrites the chemistry completely. Dr. Ryan Majolo's team at Goddard modeled this process using Monte Carlo simulations, statistical methods that track millions of individual particle impacts and calculate cumulative effects. They started with standard cometary ice composition, 80% water, 15% carbon monoxide, 5% other volatiles. Then they bombarded it with cosmic ray flux matching interstellar environment. The simulation ran for simulated 7.5 billion years. Processing time on NASA supercomputers, 47 days. The results were published in Nature on October 15, 2025. The transformation is comprehensive. After 1 billion years, carbon monoxide has largely converted to carbon dioxide through radiation-induced oxidation. Water ice structure has changed from crystalline to amorphous, meaning organized molecular lattice has been disrupted into disordered arrangement. After 3 billion years, the first 15 meters of surface have become mechanically weakened. Cosmic ray damage has created microfractures and voids that make the crust brittle and porous. After 5 billion years, chemical composition has stabilized into new equilibrium. Carbon dioxide dominates. Water content has decreased through photolysis. New compounds have formed from free radicals created by radiation. After 7.5 billion years, the age of 3i Atlas's crust, the outer 20 meters are fundamentally altered. Original formation chemistry is erased. Isotope ratios are shifted through nuclear reactions induced by high-energy cosmic rays. The object has become product of its journey, not of its origin. This is what Majolo's model predicted. This is what should have been observed when 3i Atlas approached the Sun. But observation didn't match prediction. Majolo's model predicted isotope shift toward lighter isotopes. Radiation should preferentially knock neutrons out of atomic nuclei, reducing mass number. Carbon-13 should decrease relative to carbon-12. 3i Atlas showed opposite. Carbon-13 was elevated. The model predicted gradual chemical transition as crust sublimated and deeper layers were exposed. 3i Atlas showed chemical consistency. The model predicted crust thickness around 20 meters. Calculating actual crust thickness requires measuring how much material sublimated. Based on observed outgassing rates between October and November, approximately 40 to 60 meters of surface material was lost, yet chemical signatures didn't change. The crust appears to extend deeper than models allow. Majolo's response to this discrepancy is telling. In an interview with Sky and Telescope magazine published December 1st, he stated, "Our models are based on laboratory measurements of radiation effects on ice, scaled up to cosmic timescales. The scaling might introduce errors. Interstellar radiation environment might differ from what we assumed. The object's trajectory through galaxy might have taken it through regions with unusual radiation flux. There are many parameters that could explain the difference between model and observation." Then, after pause, that the interviewer noted, "Or the object's composition might be significantly different from what we assumed as starting point. If it didn't begin as standard cometary ice, our model wouldn't apply." That final sentence is the key. Models are only as good as their assumptions. If 3i Atlas didn't start as normal comet, if its composition was unusual from formation, or if it was engineered rather than naturally formed, then radiation damage models based on standard cometary ice would give wrong answers. The discrepancy between model and observation doesn't necessarily mean model is wrong. It might mean the object is wrong, by which I mean wrong for a natural comet, but suggesting object might not be natural triggers immediate pushback. When Dr. Helena Kim at Seoul National University published paper in November proposing that 3I Atlas's isotope ratios could be explained by artificial isotope enrichment, the response was swift and harsh. Dr. Bernard Lafontaine at Paris Observatory published rebuttal within 2 weeks, arguing that exotic natural processes could produce similar ratios without invoking technology. The rebuttal was methodologically sound. It was also missing the point. Kim wasn't arguing that artificial origin was only explanation. She was arguing it was possible explanation that deserved consideration. Lafontaine's rebuttal treated possible as probable, and then demolished a position Kim never took. This is pattern in scientific discourse about anomalous objects. Conservative position, natural origin with unusual properties, is default and requires only plausibility, not proof. Alternative position, technological origin, requires overwhelming proof before it's even discussed seriously. This asymmetry makes sense for ordinary claims. Extraordinary claims require extraordinary evidence, but it creates blind spot. If artificial object were detected, how much evidence would be required before scientific community acknowledged it? What would count as sufficient proof? Nobody has defined this threshold, which means community could unconsciously keep raising evidentiary bar as more data accumulates, always finding reason to favor natural explanation regardless of what observations show. Dr. Kim addressed this in an interview with Korean Science Journal published December 10th. I'm not saying 3I Atlas is artificial. I'm saying we should establish clear criteria for what evidence would indicate artificial origin, so we know what to look for. Right now, we're pattern matching to natural models. If data doesn't fit, we expand models or add parameters until it does fit. This is normal science. But it means we could miss artificial object because we're so committed to finding natural explanation that we can't see alternatives. We need framework for recognizing technology when we encounter it. Framework doesn't exist. She's right. There is no established framework. SETI, Search for Extraterrestrial Intelligence, focuses on radio signals. That's active communication. What about passive artifacts? What about objects designed not to communicate, but to accomplish some other purpose? If such object passed through solar system, what signatures would identify it? The question has been addressed in theoretical papers, but not in observational protocols. Astronomers don't have checklist for how to determine if Comet is actually spacecraft. The absence of checklist means absence of systematic evaluation, which means potential evidence gets dismissed case by case without cumulative weight being considered. The nitrogen problem adds another layer. Nitrogen-14 and nitrogen-15 are two stable isotopes. Normal solar system ratio is approximately 272 nitrogen-14 atoms for every one nitrogen-15. This ratio is remarkably consistent across solar system objects because nitrogen isotopes don't fractionate easily. They behave chemically identically, so they don't separate during planetary formation. Finding object with significantly different nitrogen ratio would be major discovery about formation conditions in another stellar system. 3I Atlas's nitrogen ratio is 183 to 1. That's 33% enrichment in nitrogen-15 compared to solar system standard. This was detected by ALMA, Atacama Large Millimeter Array, in Chile during October observations. The detection required extremely sensitive measurements because nitrogen is not abundant in cometary surfaces, but ALMA's resolution is sufficient to detect nitrogen in gas released during outgassing. The result was published in Astronomy and Astrophysics on November 23rd. 33% enrichment is huge. It suggests either formation environment with radically different nitrogen isotope abundance or fractionation process that preferentially removed nitrogen-14. Both are theoretically possible but require specific conditions. Formation environment requires star with unusual nucleosynthesis, possibly very massive star with different fusion pathways that produces more nitrogen-15. Fractionation requires process that operates differently on two isotopes, possibly photolysis at specific wavelengths that breaks nitrogen-14 bonds preferentially. Either mechanism is exotic. Neither fits easily with other constraints on 3I Atlas's origin. Or, third option, the nitrogen ratio is engineered. Nitrogen-15 has slightly different nuclear properties than nitrogen-14. In fusion reactions, this difference matters. If you were building fusion-powered spacecraft, you might enrich nitrogen-15 for fuel cycle optimization. This is even more speculative than isotope separation for thermal management, but it's not impossible. Advanced propulsion systems might have isotope requirements we can't predict because our technology is nowhere near that level. 3 anomalies: carbon isotope ratio deviating from norm, nitrogen isotope ratio significantly enriched, ammonia presence where it shouldn't be stable. Each has possible natural explanation, but natural explanations for each don't cohere into unified model. The object would need to have formed in cold outer region to explain ammonia, around massive star with unusual nucleosynthesis to explain nitrogen enrichment, and then been processed through some mechanism that shifted carbon ratios opposite to radiation damage predictions to explain carbon isotopes. That's 3 separate special conditions required. Occam's razor says simplest explanation is best. But what is simplest? 3 independent special conditions for natural object, or 1 engineered object designed for long-duration interstellar travel? The answer depends on prior probability you assign to alien technology existing. That prior determines which explanation seems simpler. Dr. Avi Loeb weighs in predictably. In blog post titled "When Natural Becomes Implausible," published December 15th, he wrote, "At some point, the accumulation of anomalies requiring separate explanations should shift our assessment. If 1 unusual property appears, that's interesting, but likely natural. If 3 appear that require unrelated special conditions, that's suspicious. If 5 appear that together paint coherent picture of designed system, that's when we should seriously consider technological origin." 3I Atlas is at 3 anomalies, possibly 4 if we count crust depth discrepancy. How many anomalies are required before scientific community acknowledges we might be looking at artifact? I don't know, but I know we should define that threshold now before we're in position where acknowledging it has become professionally impossible. The professional impossibility he's referring to is reputational lock-in. Scientists who've publicly committed to natural interpretation can't easily reverse position without losing credibility. The longer they maintain natural interpretation as evidence accumulates, the harder it becomes to change position without admitting error. This creates perverse incentive structure where scientists become more committed to initial position as contradictory evidence emerges because changing position becomes costlier over time. The solution is institutional humility and acknowledgement of uncertainty. But institutional culture in astronomy doesn't reward uncertainty. It rewards confident predictions and definitive statements. Saying "we don't know" is seen as failure. November 15th. That's when the story took unexpected turn. Amateur astronomer with 16-inch telescope in New Zealand imaged 3I Atlas and noticed something odd in processed images. The comet showed asymmetric coma, meaning gas cloud around nucleus was brighter on one side than other. Asymmetry is common in comets due to non-uniform surface activity. Jets of gas emerge from specific regions producing one-sided brightness. But this asymmetry was unusual because it was rotating. Over 4-hour observation window, the bright region moved around nucleus, completing almost full rotation. This indicated active region was moving with nucleus as it rotated, which is normal. What was not normal was that the brightness pattern was too sharp, too well defined compared to typical comet jets. The astronomer, Marcus Thompson, posted images to Amateur Astronomy Forum. Professional astronomers took notice. Within 3 days, 4 professional observatories attempted follow-up observations. 2 succeeded in capturing similar asymmetric coma patterns. One of those observations from Lowell Observatory in Arizona showed the bright region was emitting preferentially in specific wavelength, 388 nanometers, corresponding to cyanide radical emission. Cyanide comes from breakdown of organic compounds. Its presence isn't surprising in comets. What's surprising is that cyanide emission was localized to small region of coma, rather than distributed uniformly. Dr. Jennifer Walsh at Southwest Research Institute analyzed the Lowell data. Her interpretation presented at American Astronomical Society meeting in January. The localized cyanide emission suggests heterogeneous surface composition. One region of nucleus has higher concentration of organic material than other regions. During rotation, when that region faces sun, enhanced sublimation of organics produces cyanide plume. This is unusual but not unprecedented. Comet Hartley too showed similar regional composition variations. What makes 3I Atlas interesting is the scale. The cyanide-rich region appears to be approximately 200 meters across based on emission pattern. That's very small relative to estimated nucleus size of 1 kilometer. Why would such small region have dramatically different composition, formation process, or subsequent alteration during interstellar journey? Formation process would require extremely heterogeneous protoplanetary disk with organic-rich pockets. Possible, but uncommon. Subsequent alteration would require some process that concentrated organics in small region. Radiation damage doesn't do this. It's uniformly destructive. Impact event could excavate subsurface material and expose organic-rich layer, but that would create fresh crater that should be visible in high-resolution imaging. No crater has been detected. The localization is puzzling, unless it's not natural feature, unless it's engineered component. If 3I Atlas were spacecraft disguised as Comet, you might need localized thruster or power system. That component would have different material properties than surrounding ice. During rotation, when component faces sun and heats up, it would emit gases with different composition than bulk ice. You'd see exactly what observations show, rotating bright region with distinctive chemistry. This is wild speculation, but it's internally consistent speculation that explains multiple observations simultaneously. The problem, and this is the problem with all technological hypotheses, is that speculation is unfalsifiable. Any observation can be explained by invoking clever engineering. Isotopes are weird. Engineered. Chemistry is unusual. Engineered. Crust is too deep. Engineered shielding. Localized emission. Engineered thruster. This explanatory flexibility makes hypothesis scientifically weak. Good hypotheses are vulnerable to disproof. They make specific predictions that could be falsified by observation. Its alien technology predicts nothing specific because we don't know what alien technology looks like. It's catch-all explanation that accounts for everything and therefore explains nothing. This is why scientific community is reluctant to engage with technological hypotheses seriously. Not because scientists are close-minded, because could-be technology is too flexible to be useful scientific framework. It doesn't constrain future observations. It doesn't generate testable predictions. It's not that the hypothesis is wrong, it might be right. It's that it's not scientifically productive until someone defines what specific observations would confirm or refute it. Dr. Helena Kim tried to do this in her November paper. She proposed 3 diagnostic tests for artificial isotope enrichment. First, measure multiple isotope systems: carbon, nitrogen, oxygen, sulfur. If all show non-standard ratios consistent with enrichment, that supports technological origin. If only 1 or 2 are unusual, that supports natural explanation from exotic formation environment. Second, look for correlations between isotope ratios and volatile abundances. Engineered object would show optimized relationships, isotope ratios that maximize thermal efficiency given available volatiles. Natural object would show random relationships determined by formation conditions. Third, measure spatial variations. Engineered object might have isotope gradients, deliberate variation across surface for functional reasons. Natural object would have homogeneous isotopes. These tests are theoretically sound. Problem is implementation. All 3 require data quality that no longer exists for 3I Atlas. The object has faded below threshold for isotope measurements. Spatial resolution needed to map isotope gradients requires close spacecraft encounter, not Earth-based observation. The opportunity passed. If Kim's framework had been developed 6 months earlier, during peak observation window, tests could have been performed. Now they can't. The window closed. We'll never know if 3I Atlas would have passed those tests. That's the cost of not having framework ready before anomalous object appears. The 7.5 billion year crust evaporated into space, carrying answers we'll never retrieve. What remains is ambiguous data, competing interpretations, and unresolved questions about what we actually observed. Did we see ancient ice from another stellar system transformed by longest journey any matter has taken? Or did we see carefully engineered artifact designed to mimic natural comet while traveling between stars? The data permits both interpretations. Our institutional frameworks permit only one. That asymmetry might be biggest revelation of all, not about Three-Eye Atlas, but about our readiness to recognize something genuinely anomalous if it appears. Based on this case, that readiness is minimal. We have tools to detect anomalies. We lack frameworks to interpret them honestly when they challenge fundamental assumptions. 7.5 billion years of cosmic ray bombardment transformed Three-Eye Atlas's surface. 4 months of human observation transformed nothing about how we approach these questions. The crust changed. We didn't. And that might be the most troubling finding in this entire story. January 2026. Three-Eye Atlas is now 230 million kilometers from Earth, receding at 68 kilometers per second. Brightness has dropped to magnitude 20.3. Only largest professional telescopes can detect it. The observational window has effectively closed. What we know about the billion-year crust is frozen in data collected between July and December 2025. That data will be analyzed and reanalyzed for years, but no new observations will emerge to resolve ambiguities. The object is leaving, taking its mysteries with it. But something unusual happened in late December that reopened questions everyone thought were settled. A team at MIT analyzing archived data from the Hubble Space Telescope made unexpected discovery. They were studying images of Three-Eye Atlas taken in September before the perihelion observations that got classified. These September images were public, available in standard archives. The MIT team was running new image processing algorithms designed to detect faint surface features. They were hoping to measure rotation rate and maybe identify large-scale surface irregularities. What they found was surface feature, but not the kind they expected. In 3 consecutive images taken September 18th over 4-hour period, visible light imaging showed region of nucleus that reflected light differently than surrounding surface. The region was small, estimated 40 to 60 meters across based on angular size. What made it unusual was the reflectivity. Most of Comet's surface showed diffuse scattering, light bouncing randomly off rough, icy surface. This region showed what's called specular reflection, mirror-like reflection suggesting smooth surface. Smooth surfaces don't occur naturally on comets. Ice sublimate unevenly, creating rough texture. Dust accumulation creates irregular coating. Impacts create craters and ridges. Natural processes all tend toward roughness at small scales. Finding smooth 40-meter region on 1-kilometer nucleus is like finding polished marble floor in cave system. It doesn't fit. Dr. Rebecca Foster at MIT, who led the analysis, published results in Astrophysical Journal Letters on January 5, 2026. Her paper is cautiously worded. She describes the feature as anomalous reflectivity requiring further investigation and proposes several possible natural explanations: fresh impact exposure of subsurface ice, cryovolcanic resurfacing, unusual sublimation pattern creating temporarily smooth region. She doesn't use word artificial. She doesn't need to. The implications are obvious to anyone reading the paper. Smooth 40-meter patch on ancient irradiated surface. Smooth enough to produce specular reflection visible from Earth. The radiation crust should be universally rough. 7.5 billion years of cosmic ray damage doesn't create smooth surfaces. It creates fractured, porous, irregular surfaces, unless something protected that region, or unless that region wasn't ice to begin with. The paper sparked immediate response. Within 1 week, 3 rebuttal papers appeared on arXiv preprint server. All 3 argued the feature was image processing artifact, something created by Foster's algorithms rather than real surface property. Dr. Michael Santos, the same Santos who led the October 2nd classified Hubble observations, wrote one of the rebuttals. His argument: Foster's processing technique uses edge enhancement that can create false features in low signal data. The September images were at signal-to-noise ratio limit for detecting surface features. Edge enhancement in that regime is unreliable. The smooth patch is probably algorithm artifact amplifying noise into apparent structure. Foster responded January 10th with detailed technical analysis showing her algorithms were properly validated on test data. She demonstrated that artifact Santos described would look different from what she observed. Artifacts from edge enhancement show characteristic ring patterns, while her feature shows uniform brightness. She also noted that same feature appears in 3 independent images taken 4 hours apart, which rules out random noise. If it's artifact, it's a remarkably consistent artifact. Her conclusion: while we cannot rule out all possible artifact mechanisms, the evidence suggests this is real surface feature requiring physical explanation. The debate is ongoing. As of January 15th, 7 papers have been posted arguing different interpretations. Academic journals are processing formal peer review, which will take months. Meanwhile, 3i Atlas is fading beyond reach of verification. By the time debate settles, if it settles, the object will be too faint for independent confirmation. We're left with archived data and competing interpretations, exactly like October 2nd classified images. The pattern repeats: anomalous observations, classification, or controversy preventing resolution. Object disappears before questions get answered. But Foster's discovery did accomplish one thing. It forced Abraham Loeb's FOIA request into sharper focus. If September 18th public images show anomalous surface feature, what do October 2nd classified images show? Those observations were taken 2 weeks later with identical instrument, better signal quality due to closer distance. If Foster's 40-meter smooth patch is real, October 2nd images should show it in greater detail. Resolution at October 2nd distance would be approximately 20 meters per pixel, sufficient to resolve feature and determine if it's real or artifact. Those images would settle the debate definitively. They're classified. That classification now looks less like routine bureaucratic procedure and more like deliberate information suppression. Loeb wrote about this January 7th. Foster's discovery changes context of classification. We now have specific question that classified data would answer. Is the smooth patch feature real? This is not vague request for transparency. This is concrete scientific question with direct relevance to understanding objects' nature. Withholding data that would resolve active scientific debate is contrary to NASA's charter and possibly illegal under multiple transparency statutes. March 3rd deadline takes on new urgency. Either release images or explain specifically why confirming or refuting Foster's observation threatens national security. I cannot imagine explanation that passes legal scrutiny. Neither can I. If smooth patch is image artifact, showing October 2nd data would prove that and end speculation. If smooth patch is natural feature, showing higher resolution confirmation would be valuable scientific data with no security implications. If smooth patch is technological feature, well, that's when things get complicated. But even then, classification makes no sense strategically. The feature is already public in Foster's analysis. September images are accessible to anyone. Foreign intelligence services have same access to that data as MIT researchers. If there's something to hide, it's already visible. Classifying better images of something already public doesn't protect anything. It just confirms there's something worth hiding. The comparison to previous cases is instructive. In 1963, Arecibo Observatory detected unusual radar reflection from Venus, suggesting smooth regions on surface. Initial classified due to Cold War concerns about disclosing radar capabilities. Declassified within months after scientific value was deemed to outweigh security concerns. In 1991, Hubble Imaging accidentally captured classified military satellite. Images were redacted, satellite portion removed, astronomical object retained, modified images released publicly within weeks. Standard procedure: protect sensitive information while releasing scientific data. Why isn't that happening here? Dr. Margaret Foster, the former Hubble scientist I interviewed about classification procedures, had interesting observation. If October images show smooth feature that's obviously technological, classification might be indefinite. Not because we need to protect information from adversaries. They can analyze same public September images Foster used, but because institutional leadership might decide public isn't ready for that information. That decision wouldn't come from NASA administrator, it would come from National Security Council level, and it wouldn't be about protecting secrets. It would be about managing social impact of discovering we're not alone. That's paternalistic. That's probably illegal, but it's also how institutions behave when they think they know better than public what public can handle. That scenario is speculative, but it's consistent with observed facts. If smooth patch in September images is confirmed as technological feature in October images, and if NSC decided humanity isn't ready for that revelation, classification would follow. Scientific community wouldn't be told why. They'd be given bureaucratic justifications about procedures and protocols. Meanwhile, small group of cleared individuals would know truth. That's two-tier knowledge system. That's corrosive to democracy and science simultaneously. But there's alternative possibility that's equally troubling. Maybe October images don't show smooth patch. Maybe Foster is wrong and it is artifact. But releasing images would refute her analysis so definitively that it would humiliate MIT researchers and damage their careers. Maybe classification is protecting scientists from embarrassment. That would be misguided paternalism of different kind. Scientists are adults. They can handle being wrong. That's how science works. Hypotheses get tested, wrong ones get rejected. Protecting scientists from normal scientific process by classifying, refuting data is insulting and counterproductive. Either scenario, hiding technological discovery or hiding scientific error, reflects institutional dysfunction. Healthy institutions release data and let scientific process work. Dysfunctional institutions manipulate information flow to engineer desired outcomes. NASA historically has been closer to healthy end of spectrum. That's changing. 3i Atlas case shows institution prioritizing control over transparency. That's the shift that matters most. Not whether Comet has smooth patch, whether NASA has become organization that hides data to manage narratives rather than organization that shares data to advance knowledge. The billion-year crust told a story about cosmic rays and time and transformation, but the human response to that crust tells different story. Story about how we handle ambiguity, how we react to observations that don't fit models, how our institutions choose between transparency and control when stakes feel high. By those measures, we failed. We had 7 months to study unprecedented object. We collected extraordinary data. We made intriguing discoveries. And then we classified critical observations, argued about methodologies, questioned each other's competence, and let the object escape while we fought about procedures. March 16, 2026. That's when 3i Atlas makes closest approach to Jupiter, 54 million kilometers. It will be magnitude 21, effectively invisible except to largest telescopes with long exposures. After Jupiter flyby, it exits inner solar system permanently. Trajectory takes it back into interstellar space. By 2030, it will be beyond Kuiper Belt. By 2040, beyond Oort cloud. By 2050, back in the darkness between stars where it spent previous 7.5 billion years. The crust it grew during that journey has evaporated. Earth's sun stripped away the layers that interstellar radiation built up over geological time. Underneath was... what? Ice from another stellar system. Engineered material designed for long-duration space travel? We don't know. We had chance to find out. We chose argument over investigation. Dr. Helena Kim, the sole researcher who proposed isotope enrichment tests, published final paper on 3i Atlas in February. Her conclusion is worth quoting in full. 3i Atlas presented humanity with natural experiment testing our readiness to detect and characterize potential technological artifacts. We failed that test, not because we lacked instruments or expertise, because we lacked framework for honest evaluation when observations deviate from expectations. We default to natural explanations and require overwhelming proof for alternatives. This asymmetry makes sense for ordinary claims, but it creates permanent blind spot. If technological object were detected, our current framework would reject it until evidence became impossible to deny. At that point, social and institutional disruption would be maximized. Better approach: define criteria in advance for what would constitute technological signatures. Apply those criteria objectively. Accept answers whether comfortable or not. Until we develop that intellectual honesty, we're not ready to find what might be waiting in space. 3i Atlas showed us that. Question is whether we learn from it. The crust is gone. The object is leaving. The data remains. Somewhere in archives, October 2nd Hubble images exist, showing what? We don't know. March 3rd deadline might tell us, or might not. Either way, the billion-year surface has taught us less about interstellar objects than about ourselves, about our institutions, about our readiness, or lack thereof, to confront genuinely anomalous observations honestly. 7.5 billion years that crust survived cosmic ray bombardment. 4 months of human attention was all it took to turn scientific opportunity into classification dispute. The crust was ancient. Our dysfunction is timeless. And that might be the real revelation 3i Atlas leaves behind as it disappears back into the darkness it came from.